Now, although the list implementation makes no assumptions about memory management, your program needs to make some decisions about that. Many embedded systems will pre-allocate all memory and slice it up as needed. For this example, I'll just use another set of functions included with a C standard library called malloc and free. Malloc allocates a certain number of bytes, returning a pointer to the address of the first byte. And the free function releases the memory given a pointer to some memory allocated with the malloc function. Keep in mind that the standard malloc function returns 0 if it fails to allocate the requested amount of memory. In this example, I'll just ignore that failure condition to keep this short, but you can easily introduce the appropriate defensive programming depending on what you need. These functions are declared in the standard lib header file. We'll then need to include that as well as standard I/O, that header, so that we can use printf. Now the list element doesn't actually store anything other than a pointer to the next element. In order to store something of value, we need to define our own program-specific data structure. I'll continue with my fruity theme and create an apple structure. This structure will use the list element data structure as its first member and some token value variable. This might seem contrived. The value of this approach of combining the program structure with the list element is that a single memory allocation will allocate both the list-related overhead as well as all the program-specific element data. This has many performance benefits. The important thing to remember, though, is that the list element is the first element of the apple structure, then the pointer to the list element and a pointer to the apple has the same address and can be easily converted back and forth as needed. Now let's write the program's main function and create a list of apples. This allocates the storage of the list right on the stack. We can then allocate a few apples using the standard malloc function. Now malloc knows nothing of apples, so you need to tell it how big an apple is, as in how many bytes it requires in memory. You can do so with a sizeof operator. As I said, malloc knows nothing about apples, so it returns a pointer to void, the unknown type. Placing the pointer to apple type in parentheses forms a cast, converting the pointer to void into a pointer to apple. So I now have 3 apples. Let's now give them some predictable values. So the apples are ready. Now I need to initialize the list. I use the address_of operator to pass the address of the apples variable to the list init function so that it can initialize the apples structure for me. Let's now push the apples onto the back of the list. Again, I'm using the address_of operator to pass the address of the apples variable, the list header, as well as the address of each apple's element header. Now let's walk the list and print out each apple's value. We can do this with the handy for statement. Start by plumbing up the basic syntax. Then fill in the first expression. Here, we'll just reuse one of the apple pointers to store each element as the elements are iterated. Since the list doesn't know about apples, we need to once again cast the result of list begin to a pointer to apple. Now for the conditional expression, we can simply use a to check whether a is non-zero and thus points to an apple object, indicating that the list is not empty and that we have not yet reached the end of the list. For the loop expression, we want to update A to point to the next element. Now we can fill in the body of the for statement with a simple printf function call so that we can print out the apple's value. So far so good. Now let's wrap this up by popping each element from the list so that all of the memory consumed by the apples can be freed before the program comes to an end. A simple approach is to use the while loop to loop until the list is empty. We can use the negation operator to express this using the listEmpty function. Notice that the negation operator essentially makes this while loop say, while the list is not empty, do this. Inside the loop, we start by popping an element from the list. Since we know at this point that the list is not empty, we can safely make this call. Now, even though the Apple object being pointed to is no longer in the list, it is still a valid object. You can use it, change it, add it to some other container, but eventually you'll need to free it. We can do that here by calling the free function. And that concludes our program. Let's compile to make sure we got everything right. We have one mistake. Let's see what it says here. Missing type specifier on line 70. So we can go up to line 70. And here we've misspelled type def. Let's save. Try again. And everything looks good. Using the C compiler, again everything looks good. Let's run the program. And we see printed out 1, 2, 3 as we expected. Great.